Okay, so we talked about defining a solution and what happens after something's dissolved. So now we're going to look more closely at the different types of compounds and the different types of molecules that do actually dissolve in water and how we can describe those. So substances that dissolve in water must contain ions or be polar molecules, okay? So there needs to be something that the partial charges on the water molecule, that the dipoles in the water molecule can interact with, okay? So that can either be the dipoles of another compound, or it can be ions, the positive and negative charges, the formal positive and negative charges present in actual ions. Okay, so this gives us three types of substances that will dissolve in water. The first, of course, is polar covalent molecules that can form hydrogen bonds with water. If it's able to form a hydrogen bond with water, then we can have those strong solute solvent bonds, and we will be able to form a solution with water. Polar covalent molecules that ionize, and we will look at these are actually typically acids and some bases. Okay, so acids and bases, these form ions when they react with water. And then ionic compounds that dissociate. So this is the breaking of the ionic bond in order for an ionic compound to dissolve and become a solution with water. Okay, so in this case, in case 1 and case 3, the water isn't participating in a reaction, okay? We're just having it surrounding the compounds or the charges that are already there. In the case of polar molecules that ionize, these generally ionize as a result of actually reacting with the water and therefore becoming soluble. So let's have a look at these in more detail. So polar covalent molecules, okay, these of course are substances that can form hydrogen bonds with water. There is no ions formed in these at all. All species involved, okay, are neutral, uncharged. Okay, so neutral, uncharged molecules, which means that if there are no charged particles, then these are not going to conduct electricity. So these are going to be non-conductive solutions, okay, because we don't have any formal charges or delocalized electrons. Okay, so if we have a look at this is our ethanol molecule. Of course, it contains a hydroxyl group, which means that it is able to form hydrogen bonds because we have the CH2OH, so we have the hydrogen covalently bonded to oxygen, which means it is able to form stable hydrogen bonds. So now, where we have the delta plus and delta minus on the hydroxyl of the ethanol, okay, we can form, of course, a hydrogen bond to the delta minus on the oxygen of the water molecule. And because there's strong hydrogen bond and it's a small molecule, this will drag the ethanol into solution. Of course, we can also have a hydrogen bond that would be formed to an adjacent hydrogen of a water molecule here, okay, because we can form multiple hydrogen bonds off these groups. So anything that can form hydrogen bonds to water is one way that something may dissolve. Of course, remembering that the size of the hydrocarbon tail, the non-polar hydrocarbon tail, will determine its overall solubility. Solubility is not a black and white thing of soluble or insoluble. There are scales, and as we increase the hydrocarbon chain on these, we of course would decrease solubility unless we increase the number of hydroxyls on the molecule. So other molecules that can dissolve as a result of hydrogen bonding, of course, a lot of vitamins and minerals and things like that. So vitamin C, which the structure we can see here, contains multiple hydroxyl groups. Okay, so these all can form hydrogen bonds, making vitamin C water soluble. Okay, whereas something like maybe vitamin A or vitamin K, which are our fat-soluble vitamins, they don't have as many hydroxyls, so they're not water-soluble, but vitamin C is. In the case of glucose, we have multiple hydroxyl groups hanging off the ring of glucose. Okay, these multiple hydroxyl groups, again, these are all going to be sites of hydrogen bonding. Okay, so those hydrogen bonds can form not only to other glucose molecules, but to water molecules as well. Okay, again, we can see that in the case of ammonia, where we have a NH3, okay, remembering that we now have hydrogen bonds to nitrogen, okay, which is another criteria for our hydrogen bonding. So we have covalent bonds to nitrogen, so we can form hydrogen bonds between molecules, okay, so between molecules of ammonia and water. So in this case, we have that occurring there. So that's bonding due to hydrogen, solubility due to hydrogen bonding. Okay, so now let's move on. And this is the one that we will understand a bit more once we've done acids and bases, but of course this is how acids interact with water. And this is polar covalent molecules that ionize in solutions. So we are taking a neutral covalent compound that reacts with, okay, it's reacting with water, okay, it's reacting with water to form ions. Okay, so if we take HCl, because the bond is so polarized, if we put HCl into water, it actually reacts forming H3O+, which is the hydronium ion, and the chloride ion. These ions now will interact with water molecules and will become soluble in the water. Okay, so in this case, we're talking about a compound being ionized, okay, into solution. So in this process, we start with neutral compounds and new ions are formed that weren't present before as a result of the reaction. So we would write this in the terms of HCl gas plus H2O liquid react to form H3O plus aqueous plus Cl minus aqueous, indicating that we have formed a solution. Okay, H2SO4 reacts in the same way. HNO3 reacts in the same way because these are all acids. Okay, this is not necessarily the case for something like NaOH because this is not covalent. Okay, this is actually an ionic compound with a metal and a non-metal anion. Okay, so this is not a neutral covalent compound, so it would not be deemed ionization. So essentially what's happening is when we add in the HCl, some of that HCl is reacting with water molecules forming H3O+, or some water is reacting with the HCl forming H3O+ and Cl-, but the bulk of the solution will still be water that is stabilizing these ions, and these ions dissolve into the water, forming a solution. These are the questions that relate to that. I'm going to move on to the next one, which is our ionic solubility. So when we talk about the dissociation of ionic compounds, what we're talking about is the breaking up of the ionic lattice. So in this case, where we had ionization, there was no ions present before it interacted with water. In this case, we do have ions present because we have an ionic solid. Okay, and then this is dissolving into water to form a solution. Okay, so this is the releasing of ions from the lattice, okay, into solution. Okay, so previously they were in the solid state, so they were unable to move. Now they gain kinetic energy because the ions are going to be surrounded by water molecules. Okay, they're surrounded by water molecules and pulled into solution. Okay, so they're surrounded by water molecules. In this case, because the water molecules are only partial charges, they're not formal charges, it's not a 1:1 interaction in the same, or 1:2 as it would be with the ions with an ion-to-ion interaction, it's going to require multiple water molecules to surround each ion to stabilize that charge. Okay, so in this case, what's happening is the dipoles of the water molecules interact with the ions. As they do, they pull them away into solution where they end up with what we refer to as a hydration shell or a hydration sphere, where multiple water molecules are oriented around a single ion. And then these hydration spheres, water molecules come in and come out of them, stabilizing those charges. Because normally we wouldn't see ions on their own having such formal charges. They would want to come together, positive and negative would attract due to that electrostatic attraction and form an ionic compound. Okay, but in this case, the water molecules wrap around those ions and stop them from sticking together. So when an ionic solid dissolves, ionic bonds are broken, hydrogen bonds between water molecules are broken, and new ion dipole interactions are formed. Okay, so we break the ionic bonds, we break the hydrogen bonds between adjacent water molecules, and then we form new interactions, which are ion dipole interactions. And this is how we show those. This one here is going to be an ion dipole interaction, okay, between the polar dipole of water molecules and the charged ion that has been released from the lattice. Okay, so this happens when we see zinc sulphate. If we add solid zinc sulphate into a solution, the ions dissociate, they pull apart from each other and are surrounded by water. When we look at a dissociation equation, okay, we do not put water on the left-hand side as a reactant. It is not participating in the reaction. It goes over the arrow. So we have the solid with water over the arrow goes to the dissociated ions in aqueous form. Okay, same thing now with iron chloride, iron 3 chloride in this case. That means that it will be iron 3 chloride is telling me that it's going to be Fe3+, and I get 3 chloride ions. So the solid dissociates in water to give an Fe3+ aqueous ion and 3 chloride ions, that 3 coming from the subscript in the solid. Okay, we've got 3 lots of chloride that are going to be produced when the ferric chloride dissolves. So this is the summary of what happens in terms of dissolving. Okay, so we can have the dissolving of ionic compounds. This process is referred to as dissociation. Okay, the particles present before dissolving are ions, the particles present after dissolving are ions, and we put the water above the arrow. Non-ionizing covalent compounds, so these are ones that form hydrogen bonds with water. We have molecules but no ions, and we have molecules after, still no ions. Okay, then of course ionizing covalent compounds, these are our acids. In this case, the term is ionization. Water is going to be treated as a reactant because it is reacting with the solute. Okay, we have neutral molecules before we add it into water, but after we have ions. Okay, so you need to be able to explain the interactions that are occurring in each one of these and be able to draw equations for them as well. Okay, so when we have dissociation or due to hydrogen bonding, water is not reacting, it's not changing anything about itself. Okay, so it goes above the arrow. When we have ionization, it is on the reactant side because the water also becomes ionized. Okay, so we get left with ions afterwards. And then of course these ions are going to be hydrated by other water molecules in the solution. Okay, they're going to be hydrated by neutral water molecules that are in the solution as well. They become the solute. Okay, so this is just one last little bit of writing equations for dissociation. Okay, so the equations for dissociation of ionic solids and water follow the same rules for balancing equations, so we need to make sure they're balanced. The charges of the ions must add up to an overall neutral charge, so you must know your valencies. You need to have these memorized by now. States must be shown after the dissociation as aqueous, and we show the ions that are formed during the dissociation on the right-hand side. So if we were to look at sodium chloride, we would start with sodium chloride solid, H2O over the arrow will form Na plus aqueous plus Cl minus aqueous. Pause the video, have a go at writing the one for potassium carbonate yourself, and then come back and have a look at the answer. Okay, hopefully you have written this up. We have K2CO3 as a solid, water above the arrow. Okay, we're going to get 2 lots of potassium. It's a group 1 metal, so it will be plus, and it will be aqueous, plus CO3 and carbonate has a charge of 2 minus, aqueous, and that gives us our dissociation equation for the dissociation of potassium carbonate to form a potassium carbonate solution in water. I'm going to leave this one here, and we will revisit solubility in our next video.